basically the other kinds of bonds we're going to be worried about: hydrogen, polar covalent, and metallic bonding. So if you remember, all through this, we've said any bond, whatever type, ionic, covalent, or today's new types, are forces that holds groups of two or more atoms together, makes them act like a new unit. And there's a few new ways. One of them is metallic, and it's pretty easy. It's going to be between two metals, is the main thing you need to remember. What happens is you have the positively charged nucleus of metal ions and electrons from other metal ions near them, and they attract them, and the electrons can actually move freely amongst all the different metals bonded. And that's why electrons move freely means it's conducting electricity, which metals can all do. They also conduct heat and are flexible. If you look at this picture, the blue represents a positive nucleus of metal atoms. The negatives are the electrons, and they're moving freely between all these different metals, which would be how electricity kind of works, but they are stuck together, so they're considered metallic bonds. Another nice picture of it showing the attractions between the positive nuclei and the negative electrons and electron clouds of other metal atoms. Go ahead, press pause while you put this here. Another type of bonds. We already know covalent is sharing, but we've added a word to it: polar covalent. Well, this here word, unequal sharing, two words, are by far the most important. If that's all you remember for polar covalent, you'll probably get some questions on the quiz right. Polar covalent is an unequal sharing of electrons. So basically, one atom's not strong enough to steal the electron, but it's strong enough that it hogs it. In other words, most of the time that they're flying around, it's spending more time with the bigger, more electronegative atom, like here. Hydrogen and fluorine are covalently bonded, meaning they're sharing electrons, but because fluorine is bigger, more electronegative, it's going to keep that shared pair of electrons around it more often than the hydrogen. This little sign down here, it's called delta. Delta positive means it's partially positive because it doesn't get to keep that shared electrons as much. Fluorine is partially delta negative because it gets to keep that shared pair of electrons more often. So polar covalence of unequal sharing, where the bigger atom gets to keep the shared electrons more often, or it spends more time around it. A little more on polar covalent. You feel free to Google search this and watch this, but we're going to get you through the notes quicker. I kept saying this term electronegativity. We've done some work with it, so hopefully we're familiar somewhat with it, but it's when different nonmetals form a covalent bond. They almost never share electrons equally, making them polar covalent, and the reason is electronegativity. How much of an ability does an atom have to keep electrons around it? Fluorine's the king, by the way. Here's a nice graphic. Increasing electronegativity. As we go left to right, you get more electronegative, and these numbers represent the electronegativity. And as you go down a periodic table, you get less electronegative. And really, it all starts with fluorine. So fluorine is the most electronegative. Going down from it, we get less electronegative, and going to the left, there's less. And that's one way to remember this. Fluorine's the key, it's the most, and it's in the top right corner. And I already told you about fluorine being the king. So the polarity of a bond, meaning how unequally they're shared, depends on the two atoms battling for those electrons. In fact, the bigger the difference, or the difference in electronegativity, is really determines what kind of bonds you form. A great difference, you're going to form ionic. Small difference, you're going to form polar covalent. And no difference, you're going to put non-polar covalent, or what we call covalent. Where the change is zero, meaning the two atoms have no difference in electronegativity, it's going to be a covalent bond. For the most part, when it's more than 0 and less than 2, it's going to be polar covalent, and usually over 2, it's ionic. So if you look here, electronegativity of chlorine is 3.16, hydrogen is 2.2. We subtract them, that's 0.96. That puts it in this middle range, polar covalent. This shows it's not cut and dry. There's no perfect numbers like the last screen we're talking about, but it's pretty close. Bunch of notes here, so pause while you put them in. Here's some practice examples. Identify these as ionic, polar covalent, or non-polar covalent. I is ionic, PC polar covalent, NPC non-polar covalent. So here are the differences in electronegativity, and that's what should tell you what they are. So pause this and see if you can apply what we said before the answers pop up. Remember, big differences. Over 2 are ionic. That's these two. No difference, 0, non-polar covalent, and between 0 and 2 would be the polar covalent. So that's how those were determined. Last of the other bonds are hydrogen bonds. Hydrogen bonds are considered to be what's called a dipole-dipole attraction between hydrogen and covalently bonded very electronegative atoms like nitrogen, oxygen, fluorine. So here is a polar covalent bond, just this one water molecule. Hydrogen shares an electron with this hydrogen shares with it. The oxygen is much more electronegative, so it keeps those electrons more. This one unit here would be polar covalently bonded, but this hydrogen also bonds with another oxygen. This is why you don't see a single molecule that you wouldn't even notice of water. You see big bodies of water, and it's due to that hydrogen bonding of one molecule's hydrogen with another's oxygen, and that's considered a hydrogen bond there. And we also say because of that, it's considered to have a dipole moment. It's always going to happen in these diatomic molecules with this polar covalent sharing. So we have two different types of atoms. We said this is partly negative because it's bigger, keeping more electrons than these hydrogens. And that's why we have it. And believe it or not, without hydrogen bonding, we don't have life on Earth. It's that essential to how water operates. Also, because of it, it can surround and dissolve ions. We'll learn about that later. But because it can turn its partially positive hydrogen sides around negative ions, it can dissolve them, or it can put its partially negative oxygen side on the positive ions and dissolve those as well. They're also able to stick to each other. Water can stick to each other. There's properties of water, cohesion and adhesion, that are all due to hydrogen bonding, and it's why it's able to be a liquid and a solid on Earth, essential for life. Almost every stable compound have achieved a noble gas configuration, or what we prefer to say is an octet. That full outer shell is so important to everything we do. Add this to your notes, press pause while you do, and you are good.